In this work, we address the problem of generating human cinemagraphs from still RGB images automatically using deep learning. We generate looped videos in which only the person's clothes move, as if waved by the wind. We decompose the problem into three different stages: normal map estimation, cyclic and controllable normal animation, and normal guided synthesis. First, we apply an off-the-shelf solution for normal estimation. Then, for cyclic and controllable animation, we developed a novel neural network architecture for generation of looped videos, CycleNet. Finally, we synthesize the normal video back to RGB. This is one example result obtained using our methodology. Now we will see further detail on the approach. Here you can see a more formal definition of the problem we are trying to solve. We have as input an RGB image and a wind direction as a two-dimensional unit vector on the image plane. The desired output for such input is a looped video sequence, that is, a set of RGB frames such that the animation seamlessly transitions back to the first frame. Then, solving this problem can be understood as designing and learning a function f as defined here. To solve this problem, we propose decomposing first the problem in three different stages. We start with our input RGB image in the top left corner of this slide. This is converted into a normal map using an off-the-shelf neural network for normal estimation. Then, using our novel CycleNet conditioned on the wind direction, we generate a looped video sequence of normal maps, as shown in the row below. Finally, we developed a normal guided synthesis that generates RGB frames based on the original RGB input and the predicted normal looped videos. Why we decompose the problem? Why using normal domain? The effect we want to model, that is, clothes waving in the wind, generates folds and wrinkles on the cloth. This is strongly correlated to the garment geometry, which is more explicitly represented in normal maps. Working in normal domain also simplifies the problem of generating looped videos, since this modality is invariant to lighting and appearance. Thanks to this, it is easier to train a neural network for this task, and it will present better generalization to unseen samples. Finally, in normal space, the gap between real and synthetic data is much smaller. This is especially important for this specific problem. It would be significantly challenging to obtain a large scale in the wild real datasets, since it would require sequences of perfectly still people with annotated wind data. On the other hand, generating such data synthetically is much more feasible. In this slide, we visualize some results obtained with the off-the-shelf neural network chosen for this work. As observed, the normal maps accurately capture fine geometric details on the cloth. Once we have our normal maps, we can move to cyclic and controllable animation. As mentioned before, looped video generation consisted on predicting a set of frames from our initial input frame such that the last frame seamlessly transitions to the first one. We recast the problem as an image-to-image translation, conditioned to the time difference between the input frame and the target frame. We call this also the relative time. This simplifies the problem and yields a more efficient solution. It additionally allows to train with random pairs of frames from each video. Nonetheless, it remains to be seen how to enforce a looped behavior. We apply a periodic encoding to the relative time using trigonometric functions. We use multiple components at different frequencies. We choose the frequency of each component such that the period is always a multiple of the chosen value t. This ensures a cyclic behavior with respect to the relative time, that is, the network is invariant to adding or subtracting the chosen period to the relative time. This is a detailed depiction of CycleNet architecture. It consists of a modified unit in which we condition the feature maps of the different scales to the relative time and wind direction. The input of the network is a normal map, and the output is the target normal map. The time encoding introduced before effectively maps the relative time to a set of circumferences. The wind is a unit vector, so it is already inside a circumference. The conditioning code is the concatenation of the time encoding and the wind. We apply a set of different fully connected layers to this encoding to map it to the same dimensional space as the different feature maps obtained by the unit encoder. We combine each of these encodings with its corresponding feature map by addition. Once we obtain a looped video of normal maps, we can use it for normal guided synthesis. We base our solution in intrinsic image decomposition. This technique consists of separating RGB images into a shading layer and a reflectance map. The shading layer describes the way in which the light interacts with the scene geometry. The reflectance describes the albedo color of each element in the image. Combining both layers by multiplication results in the original RGB image. We focus on the shading layer. As mentioned, it is the result of how light interacts with the geometry. On one hand, we have a set of normal maps which describe the geometry and how it changes. On the other hand, we propose a naive light model composed of directional and ambient lights. We use the shading layer obtained from the decomposition of the original input RGB image as well as the normal map corresponding to it. With this, we can estimate the parameters of our light model. We then compute a set of new shading layers for the whole normal animation. Combining this with the albedo gives us our looped RGB video. This is the data we use to train and test our methodology. On one hand, at left, we have the synthetic dataset. We simulate 3D people wearing different clothes under the effects of the wind. Then, we render the simulation results with random cloth colors, uniform or with a checkerboard pattern. By default, it is highly unlikely that the data will be looped. We use a methodology cited at the bottom of this slide to generate seamless video loops from this data. After this, all video samples will be looped videos with a duration of 5 seconds. On the other hand, we have deep fashion as our real dataset. This data contains thousands of samples of different people wearing different clothes. Here, we show some quantitative metrics obtained with this methodology, as well as variations of it and related works. Related works work by warping fields that warp encoded features to later decode them into the final prediction. Then, as variations of our method, we train CycleNet on RGB data directly, using synthetic normals and also normals estimated from synthetic RGB. One of the observations we make is that training with RGB data gives the best results on synthetic data, but cannot generalize to real data due to the big domain gap. As we move towards the normal domain, we notice a slight decrease on quantitative metrics, but better qualitative results on real data. Due to the challenges in measuring the quality of the predictions with numerical errors and metrics, we ran a user study on a random subset of predictions on deep fashion dataset. For this study, we ask about the quality of the dynamics as well as the perceived wind direction. We note that the proposed methodology using normal estimation from RGB achieves the best qualitative results. To further illustrate this, we show here qualitative results. These results also show the effect of the chosen wind encoding in the generated videos. The wind direction is represented with a green arrow. Here, we show additional results on deep fashion. Thank you for your attention. For additional details and results, please visit our project page.